Welcome to solverfy.
Okay, so for this one, we have a solenoid and we're changing the current, and that's going to cause a change in E fields, which we've seen before in Faraday's, but we're going to actually calculate the resulting electric field both inside and outside the solenoid. So let's go back to Faraday's law. So perhaps you're used to seeing it this way. And when we say EMF, we're talking about across a loop. And so EMF, just like voltage, can be written as the integral of kind of just some E dot DL, and the book uses DS, so I'll use that. And then that's around the surface. So it's sort of like a Gaussian surface, similar ideas where we're interested in the field. And then in the case of in here, within the solenoid, it's going to be like this. And outside the solenoid, it would be something more like this. So we're going to consider this line integral whose length is 2 pi r. So basically each time for the inside, that's our surface. And so you're going to get the E, sorry, let me back up. So this is minus d phi dt, and then E is equal to, E times this line integral. So the electric field by symmetry is the same everywhere along this length. So then we can just take, so we know that the product of E dot ds is not changing along the length. So we can say that this is E times 2 pi r that we're interested in. And then the magnetic flux through that surface is minus the area times the magnetic field. It's derivative with respect to time. So this is the case for within the solenoid. So this area is going to be minus pi r squared dB dt, and we're given dB dt, and just carrying this down. Therefore, we can say within, again, that if we cancel these pi's, cancel an r, then E is equal to 1/2, the magnitude of E is equal to 1/2 r dB dt. We're given that dB dt is equal to 6.5 millitesla per second. So we'll remember to do it times 10 to the minus 3 when we calculate it. And for A, R is equal to 2.2 centimeters, 0.022 meters. So plugging all of that in, I get that E is equal to 7.15 times 10 to the minus 5 volts per meter. And for part B, we're examining a position outside. I originally did not realize this, but it's because the solenoid has a diameter of 12 centimeters and we're looking at 8 centimeters from the axis of the solenoid, i.e. like kind of like a radius of 8.2 centimeters. It's indeed outside, so it's going to change things a bit, but we can still use kind of this starting point. So now for this surface, this outer one that I drew, where this left side is still going to be E 2 pi r, but now flux is only being sort of caught by a surface which has a radius, a circular surface which has a radius of the solenoid. So that's minus pi r solenoid squared times dB dt. And then so then when I plugged all this into a calculator and solved for E, I got 1.43 times 10 to the minus 4 volt per meter. I just solved the electric field and used RS equals, I guess I had to use 0.06 meters because the diameter was 12 centimeters. And then for this one, of course, I used R is equal to, what is it, 8.2.082 meters.